We built a quadcopter drone capable of remotely holding and releasing a 0.1 kilogram ferromagnetic payload.
An electromagnet gives UAVs increased effectiveness. In search and rescue, a drone equipped with an electromagnet can retrieve metallic debris from collapsed structures, clear pathways, or deliver steel tools to trapped survivors. Electromagnet drones can transport metal components easily for construction and warehouse applications. Finally, in environmental remediation, it's possible to retrieve metallic contaminants from hazardous sites.
We conducted extensive research into the physics of our product. First, a quadcopter generates lift through 4 independently controlled brushless motors. Unlike an RC plane, which has a single rotor and several control surfaces, a quadcopter achieves orientation control entirely through differential forces on the different arms, which produces torques that we control. In an X-copter design like ours, we have 2 motors spinning clockwise and 2 counterclockwise to cancel out the net rotational torque that would otherwise spin the frame. When we research propellers, we analyze the efficiency using momentum theory, which treats the propeller disc as an actuator imparting velocity to a column of air having a certain mass. We expected around 60% efficiency from our brushless motors and chose appropriately light yet sturdy materials to achieve lift. For the flight controller that we chose, this is the brain of the drone, and during flight it runs a well-tuned PID loop that corrects any deviations of the drone's orientation from the set point. And on our flight controller, PID gains are set physically using 3 potentiometers on the board. Finally, for our electromagnet, we found that the holding force is equal to the Maxwell stress tensor, and this requires soft iron as the core material due to its high relative permeability. Due to the coil's inductive switching behavior, we need a flyback protection diode to dissipate the energy. Otherwise, when the magnet is switched off in several hundred nanoseconds, a back EMF spike of potentially hundreds of kilovolts could damage the circuit. Our prototype was made out of wood and gave us an idea of the dimensions and weight we were targeting. With the electromagnet geometry confirmed, we developed a CAD model of the full drone assembly. The model was designed for the magnet to hang below the propeller plane to avoid interference, and the wire also was able to route cleanly to the flight controller without adding asymmetric weight. Here's our circuit diagram. It includes 4 ESCs connected to the flight controller motor outputs, the fly-sky receiver connected to the aileron, elevator, throttle, and rudder channels, and the electromagnet switching subcircuit. This electromagnet circuit uses a low side N-channel MOSFET driven by an Arduino Nano GPIO pin. The Arduino reads the pulse width of the receiver signal to switch on the MOSFET. A 10 kilo-ohm pull-down resistor holds the gate firmly at 0 volts between RC pulses, which prevents any false triggers. And the flyback diode is wired in reverse across the coil with the cathode attached to the positive rail. And this clamps the inductive spike to only 12 volts whenever the magnet is switched off. We were sure that everything shares a common ground with the main battery negative.
Hey everyone, so today we're going to be taking a look at our drone. Oh wait, this isn't a drone, this is a dronito. So let's take a look at our actual drone right here. So what we have in the center that controls the entire drone is this flight controller. The flight controller is connected via these 4 pins to each of our 4 ESCs. These ESCs are responsible for distributing the power as per what our flight controller tells it to. So it's a variable power source that connects to all 4 of our motors. So our 4 ESCs get their power from this PDB, power distribution board, that is connected to one of our batteries. This battery can be seen under here. We have another battery here that secures our electromagnet. So this is what we connect to power our electromagnet, and this bundle of wires houses many things such as a MOSFET, the Arduino chip, and others that help make our electromagnet at the bottom of the drone run successfully. We notice that there should be 2 wires on each side. You can see this wire is connected to this end, and on this side this wire is connected to this red crocodile clip. That is what takes the power eventually underneath to the electromagnet. One of the most crucial components on this is our flight controller receiver and this antenna, which is what receives the signals from this flight controller and transfers it into the flight controller board. So you can see that these are the connections that are connecting both of these together. The electromagnet also takes from this flight controller chip with this blue orange wire, which is what connects to this variable input which we use to control our electromagnet. So to turn on the drone, all we have to do essentially is turn on the flight controller, and then we will plug in the battery into the PDB. And now here's the tricky part. To make sure that the flight controller connects to all 4 drones, we're going to push this to the right, which is its power on sequence. And then they will start spinning. Well, yeah, I kind of cooked this one, but there we go. Thank you. Let's up the propeller just a bit. You can feel it. Electromagnet currently. No attraction. When we turn on the electromagnet, attraction, and we turn it off and it will fall.
In the process of assembling our drone and testing it, we conducted a variety of experiments that went into a bunch of the concept of electricity and magnetism as applied to our product. The electromagnetic field strength and a pole force lab characterized holding force and the number of paper clips at different energy levels, as well as other magnetic components, which directly measured the Maxwell stress tensor. And we optimized the number of coils in electromagnet against the resistance that it gave. Then we had the back EMF and flyback diode lab, which characterized the voltage behavior of the coil during switching, and we were able to see the flyback diodes by attaching an LED to the magnet's 2 ends. And then we had the potentiometer lab, where we looked at the adjustable potentiometer with the different angles, where we were able to measure the maximum resistance and therefore voltage of that went through the power source. And we also looked at how the potentiometer affected wobbling through the graphs of oscillations. We had the capacitor lab, where we checked the capacitor in the flight controller and we investigated the components of an RC circuit and how it helps stabilize power. And then we had the motor voltage lab, which measured 3-phase power delivery from the ESC and voltage and currents across the lines. And here we discovered the angular velocity by analyzing the sound frequency of the propeller spin, and the electrical power was compared to mechanical power, and we found a drop in efficiency as a result.
The first complete build revealed several areas requiring iteration before the system was flight ready. On the electrical side, we replaced breadboard connections with soldered ones and heat-shrunk exposed wires. After an accident which vaporized a pin on the flight control board, we made sure to use insulating tape on exposed metal, namely our power distribution board's bottom. Initially, our electromagnet was not reaching full strength, showing only 1 volt across the magnet. Then we realized we needed to put the MOSFET after instead of before the magnet, making a low side switch rather than a high side one. This is the correct choice because it means gate voltage is referenced directly to the ground, so gate source voltage will be high enough to switch on the magnet. We are still trying to achieve stable flight with our drone. The KK-V5.5 uses 3 physical potentiometers to set the proportional gain for roll, pitch, and yaw axis. These need to be precisely tuned to achieve an optimal trade-off between imbalance and fast oscillation. We used the manual rod test by tilting the drone with motors running at low throttle and confirming the correct motors increase speed to resist the tilt. ESC throttle calibration was completed using the KKV 5.5's dedicated pot-based calibration sequence. So this ensured that all 4 ESCs share an identical throttle range, so they respond identically to the same motor output command.